These are the notes for LT1 in the wave unit. In the wave unit, it's really sound waves that we talk about mostly, but we'll have to refer to light here at first just to set up some basic wave vocab. So when you look at the target, you're going to illustrate essential vocabulary associated with both transverse and longitudinal waves. So notice the chart is a little different than it usually is. Now we have transverse on the left column, longitudinal on the right. And I left a little space because there's some things that kind of work for both. But a lot of this should be a walk down middle school memory lane. And probably when people think of a wave, most of us think of this type of wave. Alright? And you may think water wave, which that is an example of a wave that falls in the transverse category. But this is how light travels. So one of the things you need to know are the parts and pieces of the two types of waves. So a transverse is one of them. A longitudinal wave deals with a series of compressions, which is where the medium gets pushed together, compressed, so they're areas of high density. And then a series of rarefactions. So you would have another compression, and then a rarefaction. So these areas of low density would be the rarefaction. So high and low. Sound travels as a longitudinal wave. Light travels as a transverse wave. So what you probably remember from middle school, the high points of a transverse wave are crests. The low points are called the trough of the wave. Sound waves don't have crests and troughs. They have areas where the medium, such as air, if it's a sound wave traveling through it, places where the air gets pushed together and then spread apart, and then pushed together and then spread apart. Wavelength, distance between identical points on a wave. So you can measure crest to crest. You can measure trough to trough. The symbol is lambda, the Greek letter lambda. That is wavelength. And again, it's the distance between identical points on a wave. You'll want to be sure that you're using the gizmo in this unit, and so we have chances to use the ruler on there to measure crest to crest or trough to trough, or the middle of one compression to the middle of the next compression, for example. Okay, identical points on a wave is the wavelength. Another word. Okay, this target is just filled with vocabulary. Refers to the amplitude of a wave. The amplitude is based on how much energy the wave is carrying. So, on a transverse wave, what you would do is you look at a midpoint, and it would technically be an imaginary midpoint, but we have to draw it, which makes it less imaginary. So the distance from the crest to the midpoint, or from the midpoint to the trough, those should be the same. That's the amplitude of a transverse wave. So if you have a really bright light, you would have a tall wave. A very dim light would be a short wave, okay, lesser height. A little different, obviously, for compressions and rarefactions. If you have a really loud sound, you would see extremely dense compressions. So that air, if it was traveling through, let's say, the classroom, would compress extremely tight. Okay, these are areas of high density. And so when they hit your eardrum, your tympanic membrane, which to us simple folk is an eardrum, it causes it to displace, so like push in really far. And that stimulates your auditory nerve, which is carried to your brain and perceived as some sort of sound. So a really loud sound, you get hugely tight compressions. These low density areas are really spread apart, so super low. But again, that's for sound. If it's light, it's just super tall waves. Okay, high crest, low troughs. Something you should notice about these waves is that they differ in how they are created. So on the gizmo, you see the hand travel up and down, and the wave travels outwards for a transverse wave. Okay. This would be a right angle in math class, so they're perpendicular. Okay, so the energy, let's say, would be left and right. Let's pretend it's radiant and it's light energy. Every single wave is created by a vibration. So if the electrons that vibrated to create light were going up and down, the energy would go left and right. You could flip it. Maybe the electrons are vibrating left and right. The light would be transmitted up and down. If it's a sound wave, let's say it's your vocal cords, the vibration, so as I'm sitting here talking, if the vibration that creates it is left and right, the sound travels parallel. Okay, so the energy travels left and right. Everything will be in the same plane, okay, the same direction, if it's a longitudinal wave. Now we've got some things that apply to both. All right, so maybe I'll do it like this. So both of these waves, okay, they can have amplitudes and wavelengths, but when we talk about a medium, it doesn't matter if it's a transverse wave or a longitudinal wave. A medium is just a substance that a wave travels through. So for us in sound waves, it's almost always a gas. It's the air. Okay, so a substance a wave travels through. If somebody knocks on the door, the medium could temporarily be the wood, the door itself, and then it's the air. Okay. Think about some things we know. We know that light travels faster than sound, and one of the reasons has to do with the mediums. Think about light coming through the vacuum of space. Light actually prefers not to have anything to travel through. It goes crazy fast if there's nothing in its way. But when the sunlight hits a window, for example, from the outside, it slows way down. It's hard for it to get through a medium. Whereas a sound, it has to have a medium. It needs that in order to transmit itself, which we play around with in the domino lab, which we are not to yet. But that's kind of one of the differences. But either way, a medium is a medium, so it's a substance that a wave travels through. When we talk about frequency of waves, you may think back to the electricity unit, and we talked about Tesla's alternating current, and we said at a frequency of 60 hertz. And so 1 hertz is 1 vibration in 1 second. So we talked about the switch at the power station that would flick 60 times per second. That's why we called it 60 hertz. When we talk about sound, we'll be talking about infrasonic, ultrasonic, how this affects pitch, the pitch of a sound. All right, but for right now, just knowing what frequency is enough. In the gizmo, you'll end up calculating the period of a wave. The period of a wave is the time for 1 complete cycle. So think of it as it's July. I know that's a happy thought. And you're standing out in the middle of a big lake. And when one crest hits you, if you had a stopwatch and you measured the time for the next crest to hit you. So one smashes into you, you start your stopwatch, and then you stop it when the next wave hits. That would be the period of a wave. The last thing has to do with wave speed. To calculate the wave speed, so velocity, it's the frequency of the wave, so that fancy little F is the symbol for frequency, multiplied by the wavelength of the wave. And on the gizmo, it just gives you this number, but we need to pay attention to the fact that both frequency and wavelength help to determine this velocity. There's a directly proportional relationship there, where if one of these is bigger, the speed of the wave is also bigger. All right, so a lot of stuff going on with the vocab here, but unfortunately it is somewhat of a memorization process for this target. It's a big deal because we need all of this stuff for the next 2 units to explain how is it that we hear sounds differently, how is it we see colors differently, and that sort of thing. Alrighty, good luck.